Okay, I'm excited for today. This is one of the more important class days. The stuff we do today is not only very useful for GED and getting you ready for next math class, but it's also something that the textbooks never really figured out how to explain well. So of all of the days to be in class and seeing what's happening, and this is a very good one. So starting about terms and area puzzles. And we're not going to do that immediately. We'll have a warm-up, of course. But this is something that shouldn't be hard, but textbooks and maybe previous math teachers have made it harder than it needs to be. So again, I'm glad you're here. But first, let's do our warm-up. Bring everyone to me. We have two different squares. These are two very different warm-up problems. For this one, most of these squares fit this pattern, but not all of them do. So can you find which little square is different from all of the others?
In which one?
One of these little squares is different than all the others, and maybe you can take the one I'm dragging around and use it to help you see which one is different. And I'm gonna lock these so we don't drag them. Okay. So that one's the same.
What about this one?
Those all look the same. If you let go for a moment, Gavin will make copies. So sometimes they're rotated. But that's okay. And this one is just a rotated one. Ah, Sean found it. So tell us how that one is different.
There are two different angles. There are two different triangles in there.
Yeah, it has one little triangle and another little triangle. So this square is the one that's different from all the others because it has two of those little triangles. Make sense?
Yeah.
Okay, now it gets trickier. So again, we can make a few copies of this if it helps you to drag it and rotate it and check things. In the second one, which one is not the same as all the others?
Right on. See it.
You haven't found it right away, this one here. It doesn't have
Well,
a little square inside it. Like
One.
What, well, that house is not very. Cool area. That's really bizarre. Oh, I might just have to deal with it for now. It's not letting me with my mouse down past that. But for now, I'll just go with this. Okay. Moving on, good warm up. Okay, we've seen that division creates fractions. This means that if you give me any fraction, I can rewrite it as division. I just have to take the top and bottom and put parentheses around them. And then instead of the division bar, a fraction bar, I make a division symbol. See how to turn one into the other? So that tells us that fraction bars are just sort of grouping symbols. They mean this thing on top divided by that thing on bottom. It's sort of like there's parentheses as part of it. So let's learn some tricks about that. Okay, first, we need to talk about PEMDAS. If you were taught PEMDAS the right way, there's nothing wrong with PEMDAS. But if you were taught PEMDAS the wrong way, it's gonna mean let's do what? So looking at the screen, if I do 8 divided by 4 times 2. If I'm just writing that down. Which of those is the right way to solve this? Do I do the 4 times 2 first? Because in PEMDAS, M for multiply comes before D. Or do I do the 8 divided by 4 because I'm going left to right for some reason at that point?
Multiplication is front, right?
One vote for the top, is that what I hear? Other ideas, other votes?
Is multiplication first?
Everyone's quiet, okay, only Betty is brave enough to vote here. It's actually the other way. So this one is wrong. And this is the one we want. So I need to talk about that. Do I have a slide or do I talk? I forget. Okay. Got it here. So in PEMDAS, exponents are one kind of level of things. They are what we do first. And we just saw that fraction bars. Is it not? I don't know. Leave my home. Okay, now I think, okay. So we've also seen that fraction bars is part of this first area. That parentheses, exponents, fraction bars, all of those groupings.
Many.
That's going the first thing we do. That one is too big. 1 moment. Then multiplication and division actually have equal priority. They're the second thing we do. And addition and subtraction have the third priority. If we're working in the same area, like we're only doing this top third, or we're only doing multiplication and division, or we're only doing addition and subtraction, then we go from left to right. So with the problem I gave you, 8 divided by 4 times 2, we're only dealing with the multiplication and division area of PEMDAS, so we go left to right. First, we'll do 8 divided by 4 is 2, and then we'll do the 2 times 2 is 4. So if that's new, that's not your fault, that just means that somebody taught it to you the wrong way before. The good news is there's a better way to do this. We're going to say that parentheses and exponents and fraction bars all very distinct from the rest of them. And multiplication and division we'll consider this equal priority, and addition and subtraction we're going to kind of save for last. Well, let's look at how this works. Okay. Now I'm just demonstrating, I'll bring everyone to me, but you don't have to do anything yet, your turn will come in a moment. So we're gonna think about something called terms. A term is part of an expression. Remember, all three of these things are expressions because they have no equal signs. If they had something like equals 5, then they'd be called an equation. But they don't, there's no equal signs anywhere on this page. So terms are parts of an expression. And they're separated by a plus or a minus that's outside the parentheses. There are sometimes plus or minuses inside parentheses, but that's not what we're talking about. So first, we're just going to look at these three and see how many terms are in them. So watch how I do that. I'll kind of start moving along. There's a plus, but it's inside parentheses. So I keep going. There's a sort of minus that's. So that breaks this apart where everything before is one term. And everything here is a second term. So the green expression has two terms, 1, 2. Let me do the second one before I get questioned. So 1/2 times 4 times 5, oh, here's a minus outside parentheses. So that's gonna break this apart. And now I keep going and up, there's a plus outside of parentheses, so that breaks it apart. So here I have 3 terms, 1, 2, 3. Okay, help me with the last one. Tell me when to stop moving my line. When does the first term get finished?
One. At the point.
You let me get too far. Where's the first one? Mine is not in parentheses. Right,
One.
so that breaks it. Here's 1. One more.
2,
1 more, that's a second term.
That's 2,
3,
Right after the 3, that's a third term.
and last one's.
And that's a fourth term.
4.
Everyone okay at noticing terms?
Yes.
Okay, so we could actually solve these because each of these things is now very independent of the other ones. I'm gonna pull it down where I have a little more to write about it. So that's the first one. The first term, I'm going to cover everything else. I don't care about the rest of this expression. Unimportant. Independent of. The first one. Okay, I'm gonna do that real quick. Or no. Okay, 4 plus 2, all of that divided by 3. What do I do first? Think about PEMDAS again.
Well, that's why.
So I'm gonna start with parentheses if I can.
Yeah.
So 4 plus 2, the parenthesis part, that is 6. So I will take the 4 plus 2 and say that's 6. And then 6 divided by 3, that's 2. Everyone okay with that?
Yes.
Then I'll say now the other term is totally separate from the first one. So there's a plus, I'm just gonna move that plus down the line. 8 times 2 is 16. 16 can say 16, and finally 2 plus 16 is 18. Cool. So these terms kept things totally separate on the left and the right. Cool. Whatever happened here didn't care about what happened there, and vice versa.
Okay.
Okay, anyone want me to explain that first problem in different words?
Hey David, should I go home and get some rest?
Should you what?
Can I go home and get some rest?
Yeah, if you're tired, you can go rest. We're recording. Okay, this blue one, wow, this looks big and scary. So let's see how it's actually not that bad. I'm going to start by looking at the pluses and minuses that separate the terms. So there's going to be a minus and a plus. And now I can pick which term to work with. It doesn't matter. I could start with the middle one, I could start with the left one. Most people like going left. So I will do that. So here's our first term. So what do I do first? Think about PEMDAS if it helps.
Multiplication.
I'm only multiplying, so I have to write 1/2 times 4. What's half of 4? 2. And times 5 and 10. Everyone okay with that first term? Okay, here's the second.
That's better than nothing. I don't see it all.
Okay, what goes first in the second term? The parentheses. What is 9 minus 1?
8.
Now I have only multiplication and division. They have the same priority. So I'll just go left to right. 3 times 8 is 24. And then 24 divided by 4, 6. And 10. Okay. And the last one is 5. 5. It's just a 5. It stays a 5. Nothing to. When we're all done at the bottom, now we have this addition and subtraction step at the end without anything to confuse us. 10 minus 6 is 4, plus 5 more is 9. So this is an eating an elephant kind of thing. We took something
Pretty much.
that really looked big and scary.
And side down.
That blue thing is pretty imposing. But if they ask you that on the GED, then, okay, just break it apart into terms, and each term is not that bad.
That sounds cool.
Okay, Sean's been talking a lot, so I want other people to do the talking now.
Go ahead.
Oh, whoops, I forgot to bring down my pluses and minuses. Okay, so here's this giant red one. What a monster problem. If you saw this on the GED, it doesn't mean you have to throw your hands up and go, ah, although you can. Usually 3 different rows is enough for these. I can always make more rows if I need to. Okay, 8 times 2. What's 8 times 2 for that first term?
16.
16. And that's it. I can bring 16 down more if I need because things get complicated in the other terms. This term, 14 divided by 7.
2.
2. This one is that far. We have 2 parts. Which part do we do first?
Parentheses.
19 minus 4, 15. And then 15 divided by 3.
5.
And I'll bring down the 16 and the 2. And the last term 90 divided by 9.
Is it 10?
So there we go, 4 terms, they're all simplified. Now I do the addition and subtraction. 16 minus 2 is 14. It's all addition and subtraction, so I just go left to right. 14 plus 5 is 19. And then 19 minus 10 is 9. Questions about that one? Let me move things away so you can see the whole thing at once. Okay, I have more good news, except for the GED. You're not really having to do this by hand ever. I'm not sure if I can copy and paste there. Yeah. Your calculator or a website or even Google, it can do these things for you. So the only time you have to do them by hand is if you're taking a certain kind of test. And they're asking you to do it by hand, you're not allowed to use a calculator or a website or Google. But the GED might have one like this. I would expect it's actually more like the middle one. Not quite as complicated as the third one we did. But they want to make sure you understand how terms work and order of operations. And no single part of that was too tricky. It's just sort of a slow and steady, cut it apart into pieces. Unfortunately, if I look at the book, then you can see they don't really talk about it the same way. They give you some examples, they show you how to put it in a calculator, but they don't have the nice active underlining terms kind of thing that I was able to show you now. So this would be a day where if you have these things in homework, none of these are too hard, you just have to break them apart into terms. But remember to do it the way we just did. Let's grab one more. Which one from the textbook on the screen now should I do for you?
$71.
71, okay. 71 has parentheses inside parentheses. That looks complicated, but it's actually not too bad. I'm going to rewrite it. So 3 plus 4. When you have a number next to a bracket or parentheses, then that means multiply. Okay, let me grab all of that and move it over. Went a little long. Okay, notice my font looks different than the textbook. Let me explain a few things in case they're new to you. One is that they have brackets. Brackets are just parentheses that all have parentheses in them already. Since I'm using a pen or a pencil, I can just make bigger brackets. See how mine look like they're eating the smaller brackets? That's considered a more polite thing to do. It's easier on our eyes to see that this is outside and this one is inside when you make them different sizes. But if you have a typewriter or sometimes the font of a textbook, then they don't have that option. They can't make a big parentheses here. So they use the square brackets instead. But that's all that that means. Everyone okay with that?
Yeah.
And then in two different places, they put a number next to a parenthesis or next to a bracket, and that just means times goes there. They're just being lazy and not writing the times symbol, which is legal. Okay, now let's do this. So where's my term? Here is a term. And then all the rest is a term. So I can say, well, the 3 is just going to be a 3. And now I have to do all the rest of this. What about inside here? I need to do the big parentheses first. They're the outside parentheses. They're containing all of this. And this red thing actually has 2 terms in it. Are you with me so far with that? So the 4 is hanging out front, waiting for this to be simplified. And what does this parenthesis turn into? Well, the 6 just stays a 6. On the other side, this 2 minus 0, I have to do first. So what's 2 minus 0?
2.
2. And then 8 times 3 is 16. And I'm adding them up. So I'm going to get 4 times 6 plus 16 is 24. Okay, now I'm back to thinking in green. I have these 2 big terms. The 3 is just a 3. It's still waiting for the left side, I'm sorry, the right side to get simple. 4 times 24, well, 4 20s is 80. 4 times 4 is 16, so that'll make 96. And if you needed a calculator for that, that's fine. The GED wouldn't ever ask you to do that much in your head. And then 3 plus 96 is going to just be 99. Was that one worth doing?
I will need some practice.
Yes, it takes some practice. So remember that the good way to practice this isn't to jump to the homework or the My Open Math homework, but go to the ones that have some examples and say, give me another example like that. Right. The textbook is very good at giving you different examples. Also remember that if you do want to try the homework in the book, then the odd answers, you go to tools in the top corner and supplements and then selective answers. When you click on that, you get the odd homework answers for that chapter. So it's hiding in this tools and then supplements in the middle, not videos, and selective answers. But it is something that watching me is helpful, but you really do have to practice yourself, unfortunately. Okay, now let's talk about why we care about this. So other than the GED, where they give you a long expression and say simplify it using terms, does this actually help you at all in real life? And the answer is yes, they appear all the time in area puzzles. So for now, we're just going to look at 2 different area formulas. The area of a rectangle is length times width. We've talked about that a little bit before. The area of a triangle we haven't used yet in class, I don't think. So let's talk about the area of a triangle for a moment. if I look at this triangle here. I started by drawing a rectangle. And then I drew a diagonal line more neatly than I can with my pen. To turn it into two different triangles. Everyone okay with making this triangle? So with that green triangle. If I have the length. And width of the original rectangle. So say, just as an example, that this whole rectangle. Had a length of 2 and a width of 4. Then what would the area of the whole rectangle be?
8.
8, right? Length times width. I could draw the picture. Whoops. Where. There's the 4. And there's the 2. And then if we count the pieces, there's 8 of them. Oops, that's so fast. Oh, there we go. Everyone okay with having 8 pieces there?
Yeah.
So think of these as like tiles on the bathroom floor or something. That if it was 2 feet on one direction and 4 feet on the other direction, each of these tiles is 1 foot by 1 foot, and it takes 8 of them to cover the floor. So you'll believe me though, if I say that the triangle covers half as much as the whole rectangle did. Why is that true?
It's the same length and width.
Yeah, you can kind of picture like folding it on the diagonal, or maybe taking scissors and cutting this off, and it will fit on top of the other half. If you were in class with me, I could go get some rectangles of paper and scissors, and you could cut out the top corner and see that it fits on the other corner. Are you okay with that, even if I skip that?
Yeah, I'm fine with that, Chris.
So this kind of rectangle where we're cutting the. And this kind of triangle made by cutting a rectangle diagonally, it's easy to see that the area of this triangle. Is half. Of length times width. I lost my page, okay. Now, the tricky part is what about. This other rectangle? Now my top corner isn't nice in the corner of the rectangle anymore, it's just somewhere random on the top. Is this triangle also covering half of the original rectangle? If you want, you can click on this thing here and delete it and see the hint underneath. Or just move it out of the way, either. Nicole's arrow grabbed it. Are you gonna move it or delete it? Oh, okay, so what I did as the hint is I took the piece of the original rectangle that used to be right here And then I slid it over here. Does that make sense? I took a scissors and chopped off this little bit and moved it over there. And once I did that, does it look like the rectangle is now half again?
Yes,
Hopefully you'll now believe me that this is the same size and shape as the green one. If I cut out this red top piece, I could set it down and it would cover this piece. So either way it works. Whether or not our rectangle is one of the ones where the top corner is in a square, or whether it's one where the top corner is somewhere else, rectangles are always half of the length times width that surround them. So that's where we get that formula. No one is ever going to ask you, except maybe your kids, why is the rectangle formula half of length times width? But now you have at least seen it demonstrated. It's not some magic thing. It's not like Pythagoras went up to Mount Sinai and got some magic formula. It's just how it works. Okay, we are going to find the area of these three shapes. I'll do the first one and you can help me with the other two. And we'll see how terms just appear out of this. So I'm going to scroll over to where they're all here. Okay, so first, whenever I look at one of these area puzzles, and the GED loves them, often they're not any harder than this one. I first want to make a plan that has no math at all. Because just like word problems, kind of figuring out what's up is often the hard part. So in this case, I'm saying that my shape, this house kind of shape, has a rectangle on the top. And it has a kind of square on the bottom. And if I add those two up, I get to the whole thing. So that's my plan. And I encourage you to do that. It doesn't take long to write triangle plus square. No one will grade your handwriting. And if it keeps you organized, you're not going to make a careless mistake. My next step is then to put in the formulas. So this is half of length times width. If you've learned at base times height, then that's another, oops, width I can spell. That's another way to say it. It's just that the height of the square that was containing my rectangle is what I'm calling length. And I'm also going to add for a square or a rectangle, I think this is not actually a square, length times width. Everyone okay with me just putting the formulas? That shape has that formula. This shape has that formula.
yes,
Okay, only now do I put numbers in. So half times, what's the length here? This was 10, it looks like, 10 across the bottom. And then how tall is that thing? How tall is the roof of my house? I know that this one is 18 and this one is 12.
6,
6. I have to go 6 past the 12 to get to the 18. Everyone okay with 6 for that? And then this one is just 10 and the 12. Geez. Okay, see the two terms happening? With a plus in between them. So half times 10 times 6, it's all multiplication, so M just says they just go left to right. Half of 10 is 5. 5 times 6 is 30. And then 10 times 12 is 120. And 30 plus 120 is 150. It's a area problem, so I have to label it. It was inches to start with, so I do square inches. And we'll talk about square inches more if you want, but that's not really the point of this. Okay, questions on that one now that you've seen it? You're all very quiet. Is there anyone that's done anything like this, like in the past few years? Just a little bit. This might be completely new or just not something you've done in a very long time, so it's okay if you're kind of stunned.
I'm just listening.
Okay, I'm gonna swoop things over. I have a little more space for this. Okay. This one I'm gonna get you started with and then ask you to try and do the rest and I will write for you. They're trying to be tricky by giving you this fancy, colorful 3D picture of a building. And the question is, how much sidewalk does this building have? So if I was to shade in the sidewalk around the building on those two edges, how much would I shade? But don't let the 3D colorful picture confuse you. All that's happening is there's an outside edge. That's the 113.4 on one side and 75.4 on the other. And then there's the inside edge, which is 110 and 72. And what we're looking for is this purple L-shaped area. As the sidewalk. Is everyone okay just going from the fancy picture to the less confusing picture?
Kind of confusing.
It is a little confusing.
Yeah, I'm kind of confused as well.
Same.
Let me see if I can make it a little bigger so I can draw more clearly on it. Okay, so the building itself has an edge on the front of the building where the front door is, and that edge is here. It's 110 feet side to side. Is it okay that the red lines match?
Okay.
And then the side of the building, this edge is here. My square that I'm drawing here is just like a bird's eye view going down, a floor plan of this building. So the building itself is 110 by 72. And then
Okay.
in the extra size from the sidewalk. Now the line on the outside edge of the sidewalk is a little bit longer, right? Because it sticks out this little bit right there compared to the 110. And similarly, this edge is a little bit longer because it's not only the building, it's a little bit extra right there. Do those-
David,
Yeah,
I have a question. Do they will ask for the formula or for the answer?
they'll ask for the answer. So let me show you another thing. If you go into the syllabus in the GED info, then one of the things you'll be able to see is the formula sheet. So here's all the formula we will give you in GED. You don't have to memorize the rectangle or triangle or any of these other areas.
Okay,
That's a good question.
okay. Got it. Thank you.
They might ask you to do what we just did, of take an annoying 3D picture and turn it into a floor plan. Okay, now, and Sean can talk again, he's out of timeout.
You can talk again, and you're on timeout.
I'm confused.
You're confused?
I'm
This is a
confused
kind of
on this one
confusing-
too.
Okay, well, let's skip to the next one then. That's fine. If this one just isn't working, then that's why we have more than one option. Okay, now I have 3 shapes. A red, an orange, and a green. And I want to find the area of the green one.
I would like to give you the answer for the last one, just to make sure if I'm correct or not.
Sure, let me just do it real quick then, and then you can see the process also. If I want to find this little L-shaped purple bit,
Yeah,
you have to take the big rectangle and cut out. This is a cookie cutter. I'm subtracting away the green rectangle.
I did that and I got 630.36.
That sounds right. Let me just do it real quick for recording. So I'm doing the big rectangle, subtracting away the smaller rectangle as if this is a cookie cutter, taking a bite out of it. So that's left will be the sidewalk that I care about. So the formulas are just length times width, because it's 2 different rectangles. I like writing length times width using a cursive L and W, if I'm using just letters as a shorthand. Because once in my life, I did L like that, and then it looked like the number 1, and I did a 1 instead of whatever the real number was, and I got the problem wrong, and I was sad. So I've just trained myself to use cursive L's. You don't have to do that, that's just me. So then I plug in the numbers, length times width minus length times width. This isn't the kind of thing you'd have to do by hand. You're certainly.
This is why I ask you if we need to write the formulas, because sometimes it's easy just to do the
Yeah,
multiplication.
so 13.4, whoops, let me get that. 13.4 times 75.4. So that one's 8550.36.
Yeah.
$110 times 72.
7,920.
20. And then that minus The 7920, yep, 630.36.
Good,
Did it.
okay.
And the label for this would be squares feet. Because they gave us measurements in feet. And again, we're counting not feet like on a ruler, that's a line. We're counting feet, that's placing tiles down. How many square foot tiles does it take to cover an area? Right, we were doing 8 square feet before. So that's why it's square feet, if that's enough talking about that.
Okay, thank you.
You're welcome. Okay, should I do this one also?
Yes, that other one was confusing.
Okay, the other one is too, this one is nice because we have 3 different colors. So I want to write a plan with shapes, but I don't need to find the total area. I just need to find the green area in this problem. That's. So, let me look at this shape a little more carefully. Do I know the length times width for my green one? If I could find length and width, I could just multiply them.
CN squared 2. Okay,
This is actually a very different problem, which is why I didn't start by having the steps. Let me think about this orange side. How big is that? Do we know?
it's gonna be 12 minus 8.
Yeah. This is 12. And this part is 8. So this has to be the other 4 to get to 12. Everyone see that?
Mhm.
Yeah,
This one is 4 centimeters. So now I can do this one. That I want the bottom of my green. So if
If
this
it's
much
11
is 11,
minus 4.
11 minus 4, so this has to be 7 centimeters. Everyone with me?
Mhm.
yeah,
Okay, now I'll look up and down. This part is 6. This part is 9. So what's the height of the whole thing?
15.
15, the 9 plus the 6. And so you get like. Everyone see that?
Mhm.
That's 5. So if this part is 10. Then what's this part going to be? 5. 5. So for this green one, it'll just be area. Is length times width. 35. So 7 times 5. Is 35 square. For some reason they're in centimeters instead of inches. There you go. It's just a way. That was pretty good. Pretty good. So this was a very different one. They didn't actually say, find 3 different areas and add them up. They were just, there's no terms happening. They're just. Wanting you to solve a logic puzzle. But this is also the kind of thing that might be on the GED, as far as I know. Okay, oops. Let me tuck that a little closer. Okay. Back to our doodles. Doodles. So the king of these area puzzles, if you want more practice with them, is named Noki Inaba. And if you go to a website here, then you can find lots more of them. And I think if you highlight this, you get the answer or something. Somewhere there's a way to get the answer. You can also buy a book if you want to spend money. And if you want to do one at home with your friends and family, then here's one more to do at home. Okay, we definitely need a break. So the big lessons again for the first half of this class was that you can break apart these long PEMDAS problems into terms. And each term is not too bad. And one example of when we see them in real life is when we have to put together different shapes, adding them like the house, or subtracting them like a cookie cutter for the building and the cement. Then that will make terms happen. Okay, now we get to have fun with patterns after the break. So take a little 5-minute break, stretch, get your blood sugar back. And Zoom recording. Okay, now we get a fun thing and you get to do more and not just watch me as much. We're talking about patterns. Our goal is to talk about formulas. Because there's a lot on the GED about using formulas. But we're not there yet. We're just starting with patterns. But this is more fun anyway, so that's okay. So this table has 3 columns. The first column is just counting. 1, 2, 3, 4, how many times we've done the pattern. And by convention, N is a letter that means whatever number you want. We could plug in 4, we could plug in 5, we could plug in 6, we could plug in 100, who knows? So this dot, 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 that means I don't know how many we skipped over. Maybe there's just 1 X hiding there, maybe there's 100 X's hiding there. So the dot, dot, dot is supposed to be ambiguous. Okay so far?
Yeah, but it's just Betty and Nikki back, the call's not back.
Yeah, that's okay. Did you want me to repeat that, Betty? You're still muted.
Yes, yes, please, sorry.
Okay, so this first column, placement and pattern, is just counting how many times we've done a pattern. 1, 2, 3, 4. And N is by convention, any number can go here. Maybe it's 5, maybe it's 100, it could be any number at all. So this dot, dot, dot is intended to be ambiguity. We're not sure how many little X patterns go here. Maybe there's just 1, maybe there's 1,000 of them. We're not sure, but a bunch of stuff can go in there. It's unknown. So the question for this pattern is we're making X's with 4 toothpicks in each X, right? 1, 2, 3, 4. So in the first row, 1 X, we have 4 toothpicks. In the second row with 2 X's, we have 1, 2, 3, 4, 5, 6, 7, 8 toothpicks. In the third row with 3 X's, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 toothpicks, and so on. So can you figure out in row N how many toothpicks there would be? What's the general pattern we have going on here?
Would there be 20?
Yeah, 20.
If there's a row that has 5, then yes, the number that goes 5 is 20. But N again doesn't have to be 5.
Oh,
Be 1,000. how do we get from this number to the number on the other side? What's the pattern we're seeing?
I'm seeing that it goes up by 4s.
Yeah, so that's the first thing to notice. If I'm going down, it's a +4 each time. Everyone agree with that?
Yeah. If we're going down, if the other size,
Yeah, why is it +4 each time? Because each time I'm at 4 more toothpicks. So now the next step is how do I go across from 1 to 4? Or from 2 to 8? Or from 3 to 12?
multiplying,
Mhm.
you multiply the 4 times 3.
Yeah, whatever I am doing,
Mhm.
it's gonna be a ×4 going across. 1 times 4 is 4. 2 times 4 is 8. 3 times 4 is 12. And so on. So my general rule, I will write it as y equals 4 times whatever number. Oops, make that not touch. So whatever n is, if it's 3, 3 times 4 is 12. If n is 2, 2 times 4 is 8. And so on. Everyone okay with how this works?
Yeah,
Yeah,
Can you see that the first row has 1 4? The second row has 2 4s. The third row has 3 4s. And so on. There's 1 4 for each of whatever our row number is. Okay, very nice. Now we have a caterpillar. Instead of X's. That we start with a shape that has 4 toothpicks. And now instead of making a copy of that whole shape, we're only adding 3 more toothpicks. And then when we go down again, we're adding 3 more toothpicks. And then we're adding 3 more toothpicks. And we don't have to double count what used to be like the nose of the caterpillar. So let's start by stepping down. What's the number for the pattern as we're going down?
3.
3.
3, it's a +3. Everyone happy so far?
Yes,
Yes.
Yeah,
So as we saw in the other one, if it's a plus something going down, that's going to turn into a multiply going across. But that's not quite right. It's not true that y is 3 times n. Because if I did that, 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. And that's not quite the right numbers. So what else do I have to do to fidget and fix it?
Mm.
How do I get from these numbers to those numbers? They're pretty close.
This would be wide.
Dividing's too
Add,
complicated.
add one,
Add
adding,
One.
Add one. If you're looking for where that's happening, ignore me if pictures don't help you much.
Oh, yeah.
And what's happening is. Like this wall, that's the +1.
Okay.
And then the first row has 3 plus that wall. The second has 3 and 3 plus that wall.
Okay.
The third row has 3 and 3 and 3 plus that wall. And so on. So each row gets 3 more toothpicks, but that wall was always there for all of them. So maybe that helps you, maybe that doesn't.
That's cool.
But there we go, we're getting a more complicated pattern. It's not only triple what your row number, but you have to add 1 also.
So basically adding on into it.
Okay, here's another one. This one is different. Now, if I'm looking going down, it doesn't just add a certain amount. Right, +3. +5, that's not working anymore. How do I do my pattern this time? How do I get from 1 to 1? Or 2 to 4? Or 3
Square root.
and 9. You're on the right track. I'm starting,
multiplying by himself,
yeah, multiplying it by itself. Square root would be the other direction.
Okay, so let's reverse that.
So y is n times n.
Is,
Because it's length times width, right? It's
Yeah.
3 times 3 or 2 times 2 or whatever times whatever.
so is it like, was exponential, right?
If I wanted to be fancy, maybe Sean likes being fancy. We'll write this as y equals n squared. And that's what that little symbol means, is let's make a square and on the side.
Yeah.
That's why we call it squared.
It's not too, it's like that way,
But I don't care if you write it fancy or not, this is a perfectly good way to write it.
it's close enough. That's close enough.
It's not even close, it's correct.
It's correct, yeah.
Okay, think about length times width again. Here's our last one. Last one,
Yeah,
yeah, almost last one. What's the pattern for this one? Still think about length and width. They're not the same anymore. We're not just doing squares, though.
cool. Pattern keeps changing, huh? The pattern keeps changing.
multiplying,
We are multiplying. Show me on the rectangles where these numbers go. Are they length, are they width?
are on the length,
Yeah, what, they're the bottom, what I have called length. We can debate length or width, right? So. Like that, and then how tall is it?
the wide,
It's always, how does the top height compare to the bottom? If the bottom's 2, the top is 3. If the bottom's 3, the height is 4. I will first, but how much bigger is the height compared to the bottom of each of these rectangles?
Yeah, it's different. Yeah, it's.
And no, it's always the same.
Oh. It's getting bigger going up.
Yeah, but it's always the same compared to here.
Oh, okay.
So if that's the 2, if that's the 3, how much bigger is it going up?
By one.
By 1, right? So this is 1 plus 1, this is 2 plus 1, this is 3. Whoops, I said 1 and wrote the wrong thing.
Yeah, sorry about that.
So here we have length times width, but the bottom is the row number, like 2 or 3. And then the height is always 1 more than that.
Oh, okay.
So n the times n plus 1.
I think it's fun.
Do you see it now that I've said it?
Yeah, I see it.
I'm struggling to understand it. I'm sorry.
That's okay. This is the hardest to get. So if you got the earlier ones, that's okay. I do want to give the people who are understanding a chance to show off. So this one isn't something that matters for the GED.
I'm like Nikki, I'm just good struggling to understand this too.
Me too, a little bit.
Okay. Let's see if then either
Nikki and
Betty and Nikki and Sean can see this. If we have dust floating in the air, the dust particle has weight and is being pulled down by gravity. And the amount that gravity pulls is based on the weight. Oops. The weight of the particle. And I'm going to model that by how many squares are in my dust particle. So this one is 9 squares, so on. But just like those little water strider bugs can walk on water, because they don't weigh enough to sink through the water's surface tension, the reason dust floats and doesn't just all fall down right away is that the dust particle has a bottom that is pushing against the air resistance, like putting your hand outside the window when you're driving a car. So if I zoom in on this picture, you can see that I've sort of highlighted the bottom surface as blue to represent the air resistance on the bottom of the dust particle. Now, I don't know a lot of physics. Eventually, it will be true, though, that the weight of a dust particle overwhelms the air resistance, and the dust falls. So dust particles are small, and if you have a clod of dirt, it just falls like a normal object. So the pattern for how many squares are in the dust particle, that one we saw before. The weight is about n times n, right? 3 times 3 is 9, 4 times 4 is 16, and so on. How many bottom edges are there? That's just twice the row, right? Twice 1, because left and right. Or twice 2, because it's left and right. Or twice 3, because it's left and right. So the air resistance is just double the row. And I don't know how much bigger the weight has to be compared to the air resistance. That's a physics question that I don't know. But eventually, the row times itself is going to get so much bigger than just double the row that the dust particle is going to be heavy enough to fall. Maybe that takes 100 times 100 compared to 20. Or maybe it takes 1,000 times 1,000 compared to 2,000. Okay. But eventually that will happen, because this pattern gets bigger much faster than that pattern. So using just this little bits of pattern, we can explain why it is that dust can float, that water drops can form clouds, but when they get big enough, then it rains. eventually the weight of the object overwhelms how much surface area it has on the model. So maybe that was nice to see, or maybe that was just more confusing. I'm sorry if it was more confusing.
I'm learning, like you already said.
If you want one more to work on, this is the trickiest one. And this one I'm not going to ask anyone to do because it's pretty tricky. You have to look at this and really compare it to that one. That's your hint if you want to try and do one more. You can certainly ask me about this in office hours, but not tomorrow, because again, tomorrow I have to cancel office hours because it's a teacher training day. Like Saturday 11, if you like the patterns, we could do this one. Okay, now we can really do what we meant to do, which is talk about formulas and how to use formulas, because formulas happen all the time, even on the GED. And everyone likes plugging numbers into formulas, they're not. Ready to move on, or do we need another like massage our forehead, because that was pretty intense.
You two ready to move on, or do you still wanna keep working on this one?
I don't want to do more patterns.
I don't either.
Okay, so the warm up is a pattern, but that's something we'll save for Tuesday. So the people who weren't here for this class can get a chance to look at patterns.
Okay.
Okay,
So, okay, remember when we compared equations and expressions? We said that something is named an equation if it has an equal sign in it. And if we don't have an equal sign, then we call it an expression. And terms and PEMDAS was a way to take expressions and keep swooshing the things together until it was just one number. So if I say that and you believe me, it's sort of true that I'm lying to you though.
I'm gonna make it easier on Dave, so he doesn't have to keep trying to do that. So it's back to look at his knowledge as we go for close for him.
Okay, lots of equations are really expressions in disguise. They start with a something equals in front. But nothing actually happens there. All you're supposed to do is handle the right side of the equation, plug in some numbers, and see what happens when you smash them together, just like with PEMDAS that we did a moment ago. So here's a whole bunch of formulas.
Holy cow.
All of these are things that the GED could have. If they weren't on that formula sheet, the GED would explain it to you. I'm gonna show you some you probably haven't seen before from the doctor's office in a few minutes, just because we all go to the doctor, we should know what formulas are happening in those computers.
I would think holy cow is right.
Let's pick a couple that we're familiar with. Which of these have you seen before?
I haven't seen any of those before.
Either have I.
Some of them you know about, maybe you haven't seen them written now.
I've seen area equals length times width. I've seen that before.
We just did that one, that's the rectangle area, right?
Yeah. Yes.
It's not any area, that's just for rectangles, okay? I'm sure you've seen inches as feet times 12. Maybe not
Maybe.
now, but you know that you take however many feet and multiply by 12 to get inches.
We can do fraction equals part divided by whole.
Fraction is part divided by whole, we've done that one when we were throwing things with the substitute teacher.
Okay.
Okay, so if I want to use these, then I can do that. Somebody would say, I have a rectangle. And get a pleasant gray rectangle. The length is 5 inches and the width is 2 inches, what is the area? So I'll take my length and width and plug in the numbers. And 5 times 2 is 10. And again, we don't say inches, we say square inches, because I'm imagining that I have little squares that I'm covering the surface of this thing with. So what I was talking about 2 slides ago, that nothing really happened on the left side. This word area is basically just meaning answer goes here, right? Everything that I do happens on this side. That's where I plug things into length and width and find the answer. Same thing with inches, is feet times 12. Let me see if I can find real quick a ruler.
You have to type
There's
it
a
in.
ruler. Okay, copy image. No, I don't want an ruler, I just want a ruler, okay. So there's my one ruler. Okay, why did it make a new one? I copied that one that is small and rotated, there we go, okay. So I have 2 rulers next to each other. Let's say I have, how many inches is 2 feet?
24.
So then I would say inches is 2 times 12. Two times 12 is 24, and this time the label is just plain inches. There's no square area being made. I'm not putting tiles on the floor. I'm just counting this much and that much. Everyone okay with that problem?
Yes.
And as a last example, fraction is part divided by whole. So if I say there is a brownie, let's make it a more interesting color. I'm gonna cut my brownie into 6 pieces, and Nikki gets these. Then the part that Nikki has is 2 parts. The whole brownie pan has 6 pieces. And I will write 2 divided by 6 as 2/6, part divided by whole. So in all of these, the point I'm trying to make is that the number on the left side of the, or the label on the left side of the equals isn't something I do anything with. All the work happens on that side. On these, inches is just where the answer goes, all the work happened here. Fraction is just labeling the answer, all the work happened here. Okay, so far?
Yes.
Yeah,
Okay. So here's a more I don't want to say difficult, because it's still not that hard. But a slightly bigger problem.
Well,
There's something called BMR, for basal metabolic rate. And this is how many calories your body burns when you're just lying in bed. not exercising at all. If you were to be a complete vegetable and just lie in bed all day long, how many calories would you burn?
Zero.
And on top of this, you would add calories from exercising and moving around all day. But this is an important thing that people needed to study at one point. And there's two different formulas, one for women and one for men, because people burn calories slightly differently. But the only difference, if you notice, is whether there's a +5 or a -161. Women get a boost to how many calories they burn, men have a penalty. Wow.
Oh, so basically, if I lay in bed, I burn 5 calories. And if Sean lays in bed, he burns no calories.
That's not quite, because we have to plug in the weight and the height and the age for our people.
Mhm.
And whatever those plug in, we're going to make big with multiplying. Especially this times 15.88, that's gonna make something bigger.
Mhm.
Does it make sense that the age thing is a subtraction? We burn less calories as we get older.
From age 5, no.
Age times that, but it's a minus, because the
Minus.
older you get, the fewer calories you burn, so we're taking away. Whereas if you are heavier or taller, you burn more calories as you're resting, because you're bigger, your body is doing more stuff. So Arthur and Odette are two different people, and they're three numbers. Their weight is the same. Whoops, that should be a T. Their height is the same, and their age is the same. But they're gonna plug in and be a little bit different because, oh no, they weigh. That's right. Why does weight look funny? Anyway, the problem is for height, I have to plug in inches. And 5'1" is a combination of inches and height. So if I'm 5'1", how many inches tall am I in just the inches? I have 5 feet plus one more plain inch. That's what 5'1" means. Each of these 5 feet has 12 inches. We just saw that with the ruler. So this is a 5 times 12 of inches plus one more. So 5 times 12 is 60 inches plus 1 inch. So what I really should do is cross that out and say 61 inches tall because of all of this stuff. Which I'm not drawing that clearly very well. Okay, now I'm ready to start, because I got the 5'1" changed to be 61. Everyone with me so far?
Yeah.
Okay, so let's do Odette first. The woman's formula is on top. So her BMR, her basal metabolic rate, is her weight, 110
4.55.
times 4.55 plus her height
15.88.
times 15.88 minus her age, so 30 times 5, and then at the end she gets a free +5. Notice that each of these things was its own term. I could do them separately. And I don't need the parentheses. They're written in the formula to make it easy on our eyes to see that these are 3 different things based on 3 different body measurements. But I don't really need them, right? The way PEMDAS and terms work, I'm all automatically doing these things separately from each other. I don't need those parentheses. They're just extra to be polite. And I'm not actually going to write these 4 terms separately. We've done that a bunch today. I'm just going to go to the calculator and type that all out. So 110 times 4.55 plus 61 times 15.88
minus 30
minus 30 times 5 plus the
plus 5.
So 1,324, and I'm gonna round to the nearest calorie, because none of this is that accurate. So it's about, I will be polite and make the sort of squiggly equal sign, that means I'm rounding. 1,300 and whatever it just was, 20 calories per day. So if you've seen that maybe you have a 2,000 calorie per day recommended diet or 2,500. About half of that is just what your body burns lying around. The other half is from when you exercise. If I'm trying to see Arthur, his BMR is going to be exactly the same until the end. Don't stretch it, move it. Okay. At the very end, instead of a -5, he has to have a -161. So I'm just gonna highlight all of that and paste it and change the +5 to a -160. So he's 1158.
No, he's bigger than Gordon.
So this is the kind of thing that the GED might ask you to do. It might give you some formulas that you've never seen before. You're allowed to use a calculator, and your job is to plug the numbers in wherever they go. And then smush everything together on your calculator. Does that sound okay?
Sounds about right to me too.
I want to do a highlight that the hardest part of this problem was what we did up here to get ready. How they gave us a height in feet and inches. But the formula only takes, only takes inches. So we had to do a little bit of setup. Oh. And it's kind of obvious you have to do something. You can't really plug in 5 foot 1 inches here. But what you have to do isn't terribly obvious.
Okay.
On the formula, do they tell you that there's 12 feet in an inch? No, they don't. So you might have to measure that kind of stuff. 60 minutes in an hour, 12 feet in an inch, all those common ones we do day to day. When you get closer to the GED tests, ask your math D teacher about that. So at this point, you're probably wondering, are all formulas kind of fake in the way that we just did? Where I'm plugging a bunch of stuff in on this side, all the work happens there, and this is just the answer. And the answer is no, not all formulas are just expressions in disguise. So here's an example of one that both sides matter. If you're investing, there's a thing called the rule of 72. And it says, let me make this little picture bigger so we can see it. If I take an investment and I have a certain percent that I'm getting, like my bank account gives me 3% interest. Good luck getting a bank account with 3% interest. But-
There is no,
Or maybe a certain stock goes up 6% every year.
good luck with that.
Right, that's hard to find also. Or 12%, if you're really amazing, you could find something that has a 12% change each year.
Good luck with that too.
Then the percent number multiplied by a number of years, when that is 72, 3 times 24 is 72, that's the number of years for the money to double. If I had put in 10,000, now I've doubled and I've gotten to 20. Another 24 years. And I would double again and have $40,000. This is why you need more than a savings account, by the way. Even if you wait 48 years, your money is gonna double and double again, so times 4, that's not enough to retire on. If you have something better, maybe you found some stock market investment that has 6%. 6 times 12 is 72. So now every 12 years it will double. So 12 and 12 and 12 and 12, right? These are all plus 12 each time. So now it will double then, 20,000, 40, 80, 160. Now we're getting somewhere. Although 160 is still not really enough to retire on. So in this formula, the interest rate times the years until doubling is 72. See how it's different? It's not just answer equals a bunch of stuff. If we wanted to think about it, if we put only 1,000 in a 3% compound annual interest rate place, how many years would it take it to grow? We just saw that. What's the number that goes with 3%?
Yeah, 12 years.
Now 12 went with 6%.
6%.
With
Can we?
24, with 3% it was 24, right?
24, yeah.
3% was with 24. So it's gonna take 24 years to double at 3%.
Yeah, that's not hard.
And it's gonna take another 24 years to double again. And it's gonna take another 24 years for it to double again. So that's, having only $2,000 is really not enough.
And so on,
And so on, right?
so.
So. I'm not writing it quite right though. If it was another 24, that
That's
would really
okay,
be 48.
it's late, you're tired, that's okay.
And if it was another 24 after that. Then it would be what, 60, 72.
Yeah, jeez.
So. Yeah, it takes way too long for small amounts of money to get big.
Yeah, that's like, how can you do that?
Well, the annual rate of return for the stock market. If we look at it. So. There. If we go back in the whole history. We gotta load.
It doesn't want to, it's going to sleep.
Come on, website, you can do this.
Come on, Mark said, you don't have all night, you could do this.
Oh, I think it's finding.
Can I? Let's try it again, refresh. Okay, and I do 5 years, and I do all. Yes, there we go. So here's what the stock market looks like. I'm going to steal this and put it on the whiteboard so I can show you. So just the 1-minute summary of how investing works. Overall, the stock market gets bigger. And it gets bigger at a rate of about 10% to 12% per year. Which is enough if you look at the 12% column to get lots of money and retire. The problem with the stock market is it has these crashes, right? A crash here, a crash here, crashes there, crash there, and so on, right? If you look at these crashes, then they all seem to fit within one of these 5-year colored bands. Right, stocks go down, but within 5 years, they recover. So this means if you don't need your money for 5 years, it's safe to invest that part of your savings. If you might need your money within 5 years, because you have a kid going to college, you're gonna retire and you need to spend your money, your roof might start leaking, right? Then you don't want your money in the stock market, because if you happen to put it in the stock market here and then it crashes and you need it before the recovery, then you're out of luck. So the stock market is both needed to retire safely and unreliable, because you have to be able to wait at least 5 years to get your money back. This is why people have retirement accounts. And the government and companies don't trust you to put all of your money in the stock market. Because then if you have your water boiler break and you need to replace your water heater, you don't want to have all your money invested. Not if it's at a time when it's down. But they also don't trust that you won't invest enough on your own. So your business will put some money in a retirement account for you that you don't get to touch for at least 5 years. Right? So they're forcing people to say, yeah, you're not going to have enough money to retire if you're in the 3% range, because you just have a savings account. But we also know that the stock market isn't for day-to-day money. If you might need that money in less than 5 years, it shouldn't be in the stock market. So people are trying to kind of use retirement plans to make that happen without people having to think about it. And the reason all that works is back to this purple column. You need the 12% column to really get enough money to retire.
That's about that time.
Okay, it's 7:52, I'm gonna stop the recording.